Welcome to 23rd class meeting of the spectrally correlated random processes. So last time we started to study the shift invariant subspace concept and related vectorized Fourier transform notation, where I too briefly covered the generalized Nyquist criterion. So I'm going to talk about this topic assisted by my Gemini AI assistant. So before coming to the class meeting, I've written down this one with Gemini. So it is not yet uploaded, but after the class meeting, I will upload it to the class homepage. So the final result is already given to you in the last class meeting. So we have such a result like this. So this is the key result. And this key result has simplest case that is given by this one. So here in the generalized Nyquist criterion, rewritten in terms of the vectorized Fourier transforms of the pulses, has capital K streams, while here capital K equals 1. Got it? And also, what I want to emphasize is that here appears scaling factor 1 over capital T, and that may have confused you. So today, I'm going to clear this up from the beginning. Got it? So let's take a look at the first section. So we start from this signal model, x of t, with a single stream or a single digitally modulated signal, especially following a QAM modulation scheme. So here A is a kind of scaling factor to be determined. And for simplicity, the symbol sequence D sub n is modeled as an uncorrelated or independent IID symbols with zero mean and unit variance and zero complementary variance, which means that this is a proper complex white noise sequence, but noise means somewhat confusing. So white sequence of unit power. So we don't need to care about the power spectral density of this one. Now, S of t is the transmit pulse. And capital T is the so-called symbol period, or its inverse is the symbol transmission rate. Now, the question is, what is A? That makes the average power of x of t. So here, the E means ensemble average, and bracket means time average. So this is really the power of this random process. Makes P equals some capital P. Got it? So let me not use this one yet. So do you understand what I mean? But here we have a constraint where S of t has total energy 1 normalized. Why do we need this one? And that will be seen soon. But anyway, so in this scenario, what is A? And there could be many choices as usual, probably square root P and 2 where sometimes we've seen something like this. Sometimes square root pt, sometimes square root es, which definitely not an answer because it didn't appear here. So what is your answer in this case? What I'm going to say is that number 3 is the answer. Okay. And actually, I'm going to write it like E sub s, symbol energy, but the problem is that E sub s may mean energy of s of t, so I'm not going to use it. Got it? So here, the claim is that this is a good signal model when we have unit power D sequence and unit energy S of t. Got it? And this notation is not that widely used, so you are not familiar with it, but it is very, very useful when we talk about Nyquist criteria, generalized or just a special case. And the reason is this one. We are going to use a matched filter matched to the transmit pulse for square root Nyquist criterion if you really want to clearly state. And you sample at every NT. And what you want is that this D hat has what? Desired symbol component and intersymbol interference. And you have D sub n. And what do you have? Here you have integration of S of t norm squared dt plus ISI. Now you see why I love to have, just a second, let me check the sound audio again. Check. Okay, looks okay. Check. Good. So let me continue. So here, if this equals 1, which means S of t has unit energy, then your sampled output has D sub n without any scaling effect. Got it? So you can simply say that, hey, what I want for square root Nyquist criterion for S of t is what? Is this one. Got it? So now when n equals 0, this right-hand side becomes 1. Otherwise, it's 0. Got it? That's why this strange notation with square root pt appears here, unlike most of the cases you handled for communication systems. Got it? Now, in order to familiarize ourselves with this strange scaling, let's see a very, very special example where we have flat energy spectrum for S of t. So let's consider the case where we use sync pulse for the symbol transmission. So S of t is basically a sync pulse that crosses the time axis at every t except the origin. Got it? And we know that the Fourier transform of sync pulse is what? especially when we have the symbol rate 1 over t, then it's a rectangular pulse that has non-zero value only on the Nyquist zone or Nyquist interval. Got it? Now, my question is, when we have a unit energy S of t, what would be the height of this rectangular frequency domain rectangular pulse? Right. So it must be square root t. And what would be the energy spectrum of the signal S? Squaring of it gives us the height capital T. So if we integrate energy spectrum, let me be careful. This must be norm square. So if we integrate, our integration interval, which is the Nyquist interval, has length capital 1 over t. The width is 1 over t and height is capital T. So we have unit area here. Got it? So if we write it using our algebraic form, then what do we have? We have energy spectrum equals capital T inside the Nyquist zone and 0 elsewhere. Now, since we are going to use vectorized Fourier transforms intensively, let's consider vectorized Fourier transform of this S of t. Then, usually, a vectorized Fourier transform is a vector valued signal. However, since this is band limited to plus minus 1 over t, 2t, actually, a vectorized Fourier transform is the same as the Fourier transform. And let's write this energy spectrum, then what do we have? We may write it this way, right? Vector is just element 1. Now we use inner product form. Then what do we have? We have T0 for Nyquist zone and 0 elsewhere. But when we define vectorized Fourier transform, we define the function only on the Nyquist interval. So what do we have? We have, in this case, the beautiful result like this. Got it? So I just divide both sides with capital T. And now we have unity here. Got it? So it's nothing but just scaling. But this using 1 over t appears many cases in what? In deriving the folded spectrum, in sampling a deterministic signal and finding the energy spectrum, or deriving power spectral density. So I prefer using 1 over t here. And we are going to follow this one in many, many cases of what we are going to see. Got it? So even though this is a very special case, but whenever you have some confusion, it's very nice to have a very concrete example, which you never will forget. That's why I provide you this rectangular pulse case in the frequency domain. By the way, question, what would be this value? What would be this value? Anyone? So integration of S of f gives us S of 0, right? Because S of t is the inverse Fourier transform with respect to f. And now you plug in t equals 0, which means that you have square root t times 1 over t. So this is 1 over square root t. Got it? So if we write it using sinc notation, we have 1 over square root t, sinc, capital T over capital T. That is dispersed. Got it? So this is a kind of energy normalized sinc pulse with integer multiple of t's, 0 crossing points. Got it? So now with this concrete example, let's take a look at the general case. So we consider a vectorized Fourier transform, and that can be related with the fresh vectorization. So let me write it. So we have S of t, and here is a fresh vectorizer that generates a vector valued continuous time signal. Now we can define the vectorized Fourier transform of S of t as the Fourier transform of fresh vectorizer output of S of t. Now, what is the general square root Nyquist criteria? So let me be specific. It's actually square root Nyquist criteria for S of t. And you can show that it is nothing but this one. Okay? So S of t itself may not be a Nyquist pulse, but S of t convolved with its time reversed complex conjugate, this pulse here in the derivation denoted by g of t, when sampled at every t, then you have a delta sub n. Got it? So this is the vectorized Fourier transform representation of the square root Nyquist criteria, precisely speaking. Got it? Now, what about the generalized case? So here goes the signal model for the generalized case, where we have capital K streams of QAM type modulated signal, where sequence is now subscripted by K, and transmit pulse also has subscript K. And you may say that it's a multi-carrier, but there appears no carrier, so I avoided using multi-carrier signal. These signals may overlap in time, frequency, code, and any domain. But anyway, we may have some cases where our signals can be better represented in this way. Now, what is our objective? Here, similar to what we've seen previously, we have multiple matched filters matched to each transmit pulse. So we have a bank of K matched filters sampled at the same time. By the way, if you want to have different sampling instance, then you may properly delay or advance the impulse response. Now, the output of the case branch before sampling is denoted by y sub k prime, let's say k prime of t. So you have x of t convolved with s sub k prime of negative t conjugate. And what you want is that here we only want the data symbols of the k primes stream sampled without interstream interference and intersymbol interference. Got it? So if we only have zero intersymbol interference, which means square root Nyquist criterion, then what we need is what? What we need is the repetition of the previous Nyquist criterion for all k, right? So this is the first one, kind of self-orthogonality if you want. What would be the second one? It's not that difficult to show that you have this one. So subscript is k prime, and you have k. And if k prime differs from k, then it is 0. So what can you say? You may write it here, delta sub k, k prime for all f. So actually, if you define in this way, the first one is not necessary. So this is our result. As long as k equals k prime, you have the previous square root Nyquist criterion in terms of the vectorized Fourier transform. And if k prime differs from k, then you have what? Kind of orthogonality of the vectorized Fourier transforms for all f. So how many scalar equalities do you have here, given k prime and k? Uncountably infinite. So theoretically, this criterion looks beautiful, but many people who wanted to once thought about do the research in this area hated it. They said that, hey, it's just a theory with uncountably infinite frequency, which we may not handle. And to obtain the vectorized Fourier transform, how can we use ideal low-pass filter, something like that. But point is that this fresh vectorizer and vectorized Fourier transform is a mathematical tool. It's like Fourier transform. You just Fourier transform and compute in the frequency domain, and you go back to the time domain to implement, or you may get a hint to implement your system from the intuition obtained in the frequency domain. We do the same thing with fresh vectorizers and vectorized Fourier transforms. Now, how can we very, very succinctly, simply, beautifully write this one? And the first notice is this one. This implies if we fix k prime, then here we may put all capital K vectors in the matrix with capital K columns. Now, what would be the right-hand side? What would be the right-hand side? So, if K prime is inside this 1 to capital K, then you will have all zeros and suddenly 1 and all zeros. What is that kind of vector? We usually use it as E sub k vector, which is length k vector. as a length k complex, but real doesn't matter anyway. Now, this is for k primes. What about you have all the other capital K's? Then you repeat this one and implies like this. What is this, by the way? As you learned in engineering mathematics, this can be written as what? S1 Hermitian transpose, S2 Hermitian transpose put in each row. Then you have row times matrix. And what is that? You have, am I correct? No, I'm not. Sorry about that. So here, this must be transpose. Sorry about this. Yeah. Am I right? Yeah. So this times that is the first entry 0, second entry, second column component, something like that. So it must be a row vector, right? So row, matrix, row, right? So you have this result. And what is the right-hand side? This is nothing but the identity matrix of size capital K. So eventually we have what? If we name this matrix as capital S of F matrix, we have the generalized Nyquist criterion, actually generalized square root Nyquist criterion, if I want to be precise, like this. Ready? And even though I didn't write in this document, you may generalize this one to what? You may generalize this one to something like this. So this is kind of orthogonality criteria, and this is kind of bi-orthogonality. Here, S may be understood as the VFT vectors put in the columns, VFT of the transmit waveforms put in the columns, and R could be understood as the receive filters put in the columns of the receive vectors after vectorized Fourier transform put in the columns. But here, there is a little bit subtlety because we don't have here exact scaling. Here, we assume that all the signals has unit energy. But here, even though we assume unit energy for all S, the received pulse may have different energy. But still, what we have is this one. When you want to find the scaling factor for the desired symbol, not interference, then the scaling factor is still 1 in both of the cases. Got it? Noise may be amplified due to your strange receive filter, but still you have that. Got it? That is the kind of message I wanted to convey with this simple document. And you read it carefully and try to understand all of them. That will greatly enhance your understanding about this paper. So let me quickly delete and correct some of the equations I initially started to write. So the document you've seen is kind of stemmed from my memo for this paper. And I found that, hey, something's not correct. Let me write the document again, something like that. So as you see, here goes the generalized Nyquist criterion for orthogonality, for square root generalized Nyquist criteria. And as I told you, let's consider a very large matrix S of F that has capital K columns. So each column is the vectorized Fourier transform of your case streams transmit waveform. And now, for each transmit waveform, we have unit energy condition. Now you see this is the unit energy condition, right? And we have what? We have orthogonality condition. So if K prime and K are equal and N equals 0, then you have unit value. So you don't need to scale the output to have the symbol estimate. But if you have K different from K prime or N different from 0, then you have 0. So no ISI, no stream interference. And as we've seen, that is the result. Ready? Here, I want to emphasize that this is what? Size capital K, right? Whatever bandwidth our signals have. It may be a very large, it may have very large number of rows, or it may have less number of rows than K, depending on the situation. But here we have K by capital K identity matrix. And this is not just a single equality. We have uncountably infinite equalities. Here, again, be careful. This kind of inner product type matrix multiplication is called the Gramian, the Gram matrix of S, or sometimes simply Gramian. Probably some person whose last name Gram named it long ago, Gram matrix or Gramian, or you may just regard it inner product. The reason why is that when this Hermitian transposition is not used here, but here we don't have person's name. We usually say outer product. So you may just call it an inner product of S of F, even though it's not a vector inner product. It's a matrix inner product. Ready? Now, now this is too messy. So let me give you a signal model used in this paper. Very simple. I really love simple examples. So let me just okay, what is G, by the way? I do not remember. I should have. Okay, got it. So this G sub K is unscaled quantum type signal. Got it? And we definitely assume D sub K sequence has unit power. Where is that one? Okay, let me find. Okay, mean 0 and variance 1. okay, and proper complex. Got it? Proper complex zero-mean unit variance, and probably it consists of uncorrelated random variables. So it's a white sequence, proper white unit power sequence. The same as what I just told you. Got it? And here our transmit pulse or transmit waveform is assumed to have strict sense bandwidth W/2 in complex baseband. And actually, this is a complex baseband notation. So in passband, we are going to assume that the signal occupies W hertz in real passband. Got it? When it is down converted, right? Bandwidth W becomes bandwidth W/2. And here, the multiple streams have the common symbol rate. This is very tricky. As you've seen, Dr. Yehun Yoon's paper, co-authored by me, assumes we have more variety in selecting these transmission rates for different K, even though there still were restrictions like the T sub Ks must have common multiple or something like that. But here, we assume that all the signals have the same symbol rate. And W times T, this is sometimes it's called bandwidth time product or BT product. But I usually don't like to use B, so I love to use WT product. And this WT product, so W, bandwidth in passband, T, the transmission, symbol transmission rate. Now you multiply these two, you have unit list or dimensionless quantity. And this quantity is very interesting. Why? Because if you consider single stream, what is the minimum bandwidth required to have zero intersymbol interference in the signal? Your system bandwidth or signal bandwidth of the transmit pulse or overall received pulse must have what? Bandwidth time product greater than or equal to 1. Am I right? So greater than or equal to 1. So if you have K equals capital 1, this inequality must be negated. So WT must be greater than or equal to 1. So this paper assumes very strange case. You have capital K streams and their entire bandwidth W times symbol transmit rate is less than capital K. So on average, none of the stream occupies bandwidth greater than or equal to the minimum bandwidth, right? So this is a very strange scenario. And the paper is talking about very strange scenario of so-called overloaded CDMA system. And this research is kind of done a decade ago, but now similar ideas comes again and again when people talk about faster than Nyquist transmission and when people talk about non-orthogonal multiple access. Actually, this is the simplest form of non-orthogonal multiple access where user signals are optimally shaped, pulse shaped, so that their interference to other stream is minimized in the overall sense. And what kind of that overall sense is used will be introduced soon. So do you have the idea now? So the simplest, most simple case is a single stream case where you have less than Nyquist minimum bandwidth. That is exactly faster than Nyquist transmission. So FTN, abbreviation of faster than Nyquist, is often very, very misused terminology. If you find 100 papers having FTN in the title, 98% of the papers have misleading definition or no definition, no precise definition about what is really a faster than Nyquist transmission. And what I define is that WT product is less than 1. So W is the bandwidth in passband, if you consider passband signaling, and T is the symbol period. And if this product is less than 1, I define the signaling is faster than Nyquist transmission. The problem is that 98%, if I say, I didn't count, so it's just an arbitrary number. But anyway, it means many, okay, majority, has serious problem. What they do is that they just choose a square root Nyquist pulse for symbol transmission T, transmission period T. So for example, if they choose square root Nyquist pulse, then what do they have? They have this beautiful shape, right? Let me just use magnitude square, right? Raised cosine in the frequency domain. The problem is that they do not use this capital T, supposedly to be used for zero ISI. What they do is that they have some strange notation like this. Sorry about that, gamma T or alpha T. Am I? No. Sorry about that. I forgot their notation. Got it? So if alpha is greater than 1, what happens? Your symbol period shortens. Got it? So if alpha is 2, what does that mean? Even though this pulse is designed for the transmission rate 1 over capital T, actually it is used for the transmission rate 2 times 1 over capital T. And what people say is this one. Okay, let's consider square root Nyquist pulse, whether it's a square root raised cosine or not, that is designed for some transmission rate capital T. Now, if we use this transmit pulse for the transmission faster than that originally targeted rate, then we have faster than Nyquist transmission. I really hate that definition, because if we want to derive any communication theoretically sound, which means making sense result, this is not good. The first reason is that why from the beginning we choose a square root Nyquist pulse for some specific transmission rate? We don't need that, right? We don't need that. What makes sense is the first one. Compared to the minimum bandwidth required, are we really transmit faster than the required transmission, the minimum maximum transmission rate or not? Got it? And interestingly, Dr. Yehun Yoon's paper exactly covers this problem with single user faster than Nyquist transmission. When we have zero, when we have flat channel. So here again, this paper looks very similar. So we have a flat channel in complex spacebands. It could have delay, but it doesn't matter. It could have some phase rotation. It doesn't matter. Anyway, the channel is frequency flat. For the simplicity, you may say that these are all ones, right? And thetas are all zeros. It doesn't matter. And what was the result? What was the interesting result of Dr. Yehun Yoon's paper about this case for faster than Nyquist transmission? So you need optimality criteria. Suppose we want to minimize the ISI power in our received signal. What does that mean? We may maximize the signal to interference plus noise ratio, or we may minimize the mean squared error in our estimation. Got it? And the result is strikingly simple. For the very special case, the optimal pulse is what? Still flat. It's a sync pulse. And I have to say that one of the optimal pulse. Got it? So in order to clearly state, let me mark this point as 1 over 2t. And this point as w over 2. So in passband, what is the bandwidth? Bandwidth is w. What is the transmission rate? Transmission rate is this one. So w is less than 1 over t, which means wt product is less than 1. And you may wonder why this strange optimality of sync pulse. And that could be answered in this paper, even though we have capital K streams. Because if you choose capital K equals 1, you have the result. So the papers are very closely related, actually, even though this apparently have multi-user scenario. And Dr. Yehun Yoon's paper is about multi-user, multi-rate scenario, but they share a lot of similar results. So let's see. We have this signal, and we have here goes the normalization. E sub s is the PT, what you've seen. Got it? Since we now normalize the transmit pulses energy as 1, so we need to scale with square root PT to make everything simple. And the channel does not amplify or diminish the amplitude, so they are frequency flat channel, flat unit height in the frequency domain. And these signals are summed and corrupted by the noise. And this is the most ideal continuous time version of so-called multiple access scenario. So you have a single, for example, base station, and you have many different mobile stations. And they transmit signal without multipath. Got it? So as you see here, in order to have some idea what's going on, people assume very simple models, very simple channel models. So whenever you see very simple channel models, a paper has very simple channel models appearing in a prestigious journal, you may say that, okay, it's a very theoretical paper. Okay. Anyway, so in the receiver, our received signal R of t is processed in which way? In the MMSE sense. In the previous generalized Nyquist criterion, we assumed matched filters. But matched filters is not always optimal in some other criterion, in other sense. So here, we use linear receiver, and we want to minimize the mean squared error at the cased output. And you can see that due to the cyclostationarity, M's symbol's mean squared error is the same as any M prime's symbol's mean squared error. So this is just named with parameter K. And we may define SINR, and this may look strange, and you may not love it, but anyway, expectation is something, but here goes the absolute value, so you may hate it, but anyway, just to focus on mean squared error first. Ready? Let's talk about this later because it's confusing yet. The problem is that since we have capital K multiple access user signals, there are capital K performance metrics. So in nature, this is what? This is a multi-criterion optimization problem. And usually, whenever you hear multi-criterion multi-objective optimization, it's hard to solve. One of the simplest approach is to consider total mean squared error minimization. So sometimes we just add up these mean squared errors. So sum up for all K, and then we minimize. In this paper, we adopt that criteria. Okay? So you may say that, okay, problem becomes simpler and simpler. The problem of sometimes this kind of simplification gives us very trivial result. So we are disappointed as a researcher because solution is trivial. But wait, we have no trivial solution. So the optimization problem is very simple. We are going to jointly optimize transmit and receive waveforms, S sub k and W sub k. And here is the total mean squared error. And here goes the energy normalization. We don't need a squaring it because it's anyway unit value, right? So it's same as the unit energy condition. So problem is very simple. Then let me ask you a question. What's the difference between this problem from that 2004 paper where we assume we wanted to perform joint transmit and waveform optimization? What's the difference? There, we assume the noise plus the received signal is corrupted by a cyclostationary interference. So situation may be the same. We may target to a single user in this case, in that case. But what's the difference? Now the desired, for example, first, transmit and receive waveforms to be optimized, assuming that all the other users do not change their waveform. Of course, in one of the subsection of that 2004 paper, I assume kind of a two-person game by changing the first pair's TX-RX waveform and then second user, and they take turns, and what would be the converged result compared to the optimal case. But this is different. Here we have white noise. N of t is white Gaussian noise. And now we have capital K transmitters and single receiver with capital K receivers. And the total mean squared error is to be minimized by optimizing all the transmit and receive waveforms. Got it? So you see the difference. Now, whenever we have mean squared error, we have almost the same result as 2004 paper actually. That's why I tackled this problem. If you read the paper, I, as one of the authors, talk about the result in so-called synchronous CDMA society. So when people studied multiple luxes, they loved CDMA because TDMA and FDMA looked too simple. Every signals are already orthogonal. So even though problem has multiple access, it reduces to separate single user access problem. Nothing to be interesting. So they consider the case where each signal interferes. And that is not only just mathematically, theoretically interesting, but also the key for the 2.5 generation cellular system, CDMA1 by Qualcomm and ATRI, or Korean Research Institute and companies, and 3G, third generation WCDMA. The problem is that the synchronous CDMA, which generated interesting results, mathematically beautiful, theoretically impressive results, were far from reality, the continuous time signals transmitted by cellular systems. So this paper wanted to bridge the gap between this reality with all continuous time signal models and synchronous CDMA result. So as you see the title, those synchronous CDMA guys found Welch-bound equality sequences. Probably you've seen in one of Professor Kyung-Chul Yang's course on sequences, if he provided the course recently and you have taken it. But anyway, this is one of the most important set of vectors. People say sequences, but actually set of vectors. But this was for synchronous vector-valued model. And the paper extends for the continuous time. And the procedure is very similar to 2004 paper. That's why I could write it. So let's see. You see something very similar, right? And what we do is that we usually convert this type of inner product using what? Vectorized Fourier transforms, and then in the frequency domain. We exploit cyclostationarity. So whenever we have infinite sum, that's good, right? Because we know how to handle that. And suddenly we have, as I told you, vectorized Fourier transform of the K's received waveform, vectorized Fourier transform of K primes transmit waveform. And that looking horrible mean squared error now can be written very compactly in the frequency domain in terms of the vectorized Fourier transforms. See that? You've seen something very similar already in 2004 paper. You have received signals, matrix valued power spectral density, and you have received waveform, makes the quadratic form, and then you have real part and desired component, desired signals transmit waveform, and your received waveform, something like that. Got it? So this is actually exactly the same as 2004 paper because all the other interference is here already, including the desired signal component. So total mean squared error is just the summation of this for all k. So you have, instead of 1, you have capital K, and you have summation of this integral on the Nyquist zone. The problem is that we want to optimize not only WK, but not only SK, but also all the other WKs and SKs inside this one. So it looks horrible, but if we just define this S matrix containing all the vectorized Fourier transforms of S, then we may rewrite it this way. Okay, where it is. By the way, this is nothing but the 2004 paper extended with K signals. So the procedure is almost the same. We first optimize receive filters, assuming the transmit filters are given. And interestingly, this mean squared error minimization at each receive output can be done separately because the mean squared error minimization given transmit waveform is not affected by the choices of other receive waveform. So we plug in this one to simplify our mean squared error for the minimized mean squared error at the receiver, but not yet minimized for transmit waveforms. Now, in terms only of transmit waveforms, because here, this is now replaced by that one. So the procedure is very, very similar to 2004 paper. And total mean squared error is now can be written this way after receive optimization. And here comes the famous relation between linear MMSE receiver outputs mean squared error and SINR. You have to remember. Now here comes the transmit optimization. And from this point, actually, I and co-authors borrow the ideas of their synchronous CDMA people. Because now we can optimize at each F. At each F, we just have almost the same problem as the synchronous CDMA guys, where they have only a single set of vectors, not parameterized F. But as you've seen in 2004 paper, the trick is that at each F, we need to assume some energy allocated that frequency F for the case signal. So we have to introduce A sub k of F. Here, A sub k is the probably total energy. So as you see that, it's a summation of the total energy at frequency offset F, where F is defined inside the Nyquist zone. So we have not just a simple optimization that can be done using the result from synchronous CDMA guys, but also we had to optimize A of F. And to optimize this A of F, the trick is that, hey, let's assume that A sub k of F's are chosen somehow, and then let's find optimal S sub k's first. And then let's remove the effect of our choice. We may find the minimized mean squared error in terms only of A sub k's, and then we optimize with respect to A sub k. That's the idea. So here goes that problem. Now we have only A sub k. And eventually we have the optimal solution. So A of F, here this is not complex conjugate, it's a optimal something. So this means optimal. And it's just simple optimization using the result. And here goes the result. So let's take a look at this one. I wrote the answer in this way. Probably I should have written that way, removing this t, right? So 1 over t, and what is this? Is it Gramian or outer product? It's outer product, be careful. It's not the inner product appeared in the generalized Nyquist criteria. Now, outer product equals what? Scaled identity matrix, but be careful. This identity matrix is not K by K because it's not equal to the Gramian matrix. This is what? Size varying matrix if we do not include some strange orthogonal projection matrices. So here, N of F is the called degree of freedom in our design at frequency F, and its definition and derivation takes up here and its meaning. Interestingly, this capital N of F integrated over the entire interval and multiplied by t, then it becomes n. So this is just the average degrees of freedom. And n is, you can see, is the same as Wt. So if you are given a bandwidth W and you are going to use symbol period capital T, then your N of F averaged over this entire interval. So it may look strange, but see that? This is actually N of F, df, integrated. And what is the entire length of interval? 1 over t. So this is the degree of freedom summed over, and this is kind of all the frequency intervals number, even though it's a length. So on average, this is n, and we can show that it's same as Wt. So we are not creating new dimension. When we are given Wt, that is the unitless degree of freedom in our design. And we divide that degree of freedom, Wt, at each f in some rule that is that size varying length of the vectorized Fourier transforms. Anyway, so let me go back. So here is a strange size varying identity matrix, I sub n of f. And here goes the scaling factor. And let's see what it is. So whenever we have confusion, then we simplify. So the simplest case is what? Capital K equals 1, right? When capital K equals 1, what is our result? Our result must be this one, right? And do we have the same result? And it may look strange, but when we have only one vector, then we have the outer product equals 1 over n and n of f. And what do you want to do with this one? This implies if we take the trace, then what happens? If we take the trace, these two vectors can switch the order, right? You know that trace of AB is trace of BA when the sizes of the matrices allow the multiplication, right? So if we take the trace, then the left-hand side becomes that one. What about the right-hand side? What about the right-hand side? Trace of identity matrix with size n of f. Then we have n of f, right? So this becomes, sorry, you need to be careful. Trace, yeah. So So right-hand side becomes this one. And if I remember correctly, so this result allows only when WT product is less than or equal to 1, right? So if I remember correct, this N of F is always 1. So this becomes, let me see. Yeah, just a second. What is N, by the way? N is the average, right? N is WT. Yeah, this is WT, if I remember. And N of F is 1. Is it 1? It is 1, sometimes 0. Okay. Be careful. Okay. The reason why this is confusing is that generalized Nyquist criterion requires WT greater than or equal to K. And this result requires WT less than or equal to K. So they only have the same solution when WT equals K, especially when K equals 1, WT equals 1. So this is WT, and in our simplest case, this is 1. And size is 1, so we have the right-hand side. Got it? So they have only one contact point. Anyway, so derivation is very lengthy, and here goes the interesting part. So even though we considered linear MMSE receiver, the sequence guys, sequence design researchers already have shown that Welch-bound equality sequences have very interesting property. That is, that the sequences, the vectors overall, altogether minimizes total squared correlation. And what is the total squared correlation for the vectors? So suppose you have capital K vectors, and the total squared correlation equals the inner product between two vectors squared and summed over. Got it? By the way, K prime. So two different or same sequences are chosen, selected from capital K, and you compute the inner product. It could be very large when K equals K prime. It could be very small when K differs from K prime. And then you take the magnitude square, and then you sum up. This is total squared correlation. And this metric includes what? Actually, desired signal power and all the intersymbol interference type interference. So if we generalize this total squared correlation, we have this one. See that? Now we have infinitely many symbol estimates sampled at every t. So this is the received output sampled at LT. It's squared and summed over for all L, the delay, and summed over for all K and K prime. So this is exactly the total squared correlation generalized for this continuous time model. And now, what if we just forget about our total mean squared error performance metric, but adopt this total squared correlation metric? And again, the solution is the same. What we have is this one. Our vectorized Fourier transforms must satisfy, where it is, must satisfy this condition. Got it? Outer product of the matrix that contains the vectorized Fourier transforms must be proportional to identity matrix with proper scale. And still, we have no idea what does this mean. So the paper specializes and shows very interesting result, and people really loved these examples. And the first one is that there are many solutions. So the optimal solutions cannot be all enumerated. As we already know, slight change of phase gives us infinitely many solutions. So among the optimal solutions, the authors show 3 representative results. First one is FDMA type solution. The interesting thing is that, as the next figure shows, this is the entire frequency band W. And now we assume the Wt is less than K. So W divided by K is less than 1 over T. So this width assigned for each other, for each FDMA user, is less than 1 over T. What is that? Each transmission is faster than Nike's transmission. And as you see here, each optimal pulse has what? Frequency flat, sync type pulse. And if we derive the result due to the self-interference, but no interstream interference, we have performance limit in the mean squared error. And let's sum up all the mean squared errors. Then we have that minimized mean squared error. Second one is that let's consider TDMA type solution. And this is really interesting. So what we do is that in the time domain, each stream transmits at every t. But now they divide the time somehow. How? This is for the first user. That is for the second user. That is for the case user. If we have Wt equals K, then our solution is the sync pulse that is optimally spaced. So at the optimal receive filter, there is no ISI. Now, these sync pulses is not the zero ISI pulse. It has wider bandwidth. So each pulse gets all the interstream interference. And interestingly, the total mean squared error is the same. Individual mean squared error is the same. What does that mean? Even though those overloaded CDMA researchers in vector discrete model, they had no idea what they were doing. Actually, they were designing system like this. So they were actually proposing FDMA system, exactly separated in the frequency band, but all the interference was from itself, each user. Or all the interference is from this time division, not perfectly divided multi-access users. And of course, we can design CDMA users similarly. So this paper gave an idea like when we have non-orthogonal or overloaded multiple access, actually, we should ask ourselves, there could be simpler way to have the same performance, right? What do you want to do when you are asked to design non-orthogonal multiple access system? Do you want to have very complicated receiver? Or you may design FDMA type system that has no other interference except its self-interference. That is the implication, that was the implication of this paper. And when I presented this result in the conferences, people just said, very interesting. The problem is that still it's too theoretic, as you see. Got it? So this Wednesday, we are going to see this paper where I just dig up more with this FDMA type solution. So in this paper, there is no cyclostationarity at all. So I'm going to just give you an idea of what is the result, and we'll move to more important topic. But here, since now you have FDMA restriction, what is good? The transmission rates of each user signal may totally different. They do not need to have common multiple. They do not need to be the same, right? In FDMA, all the interferences are ideal, in the ideal case, are nulled out. And in this case, we try to design a more complicated system in a more realistic scenario. But anyway, that is all for the day, okay?